Hi, everybody. My name's Charlie Engelke, and I'm CTO of Infotech Inc., a company in Florida that makes application software for vertical industries. And as CTO, part of my job is to scout out new possible technical solutions to problems we're encountering or may encounter before we have to commit time and have a schedule and a budget on a real project. And sometimes I do that with an entire team. Sometimes I do it just by myself. And to that end, last summer, I set a goal to figure out how we can best protect messages going between two different browser users through our intermediate servers. Protect those messages from being disclosed, even to us, or tampered with by anybody. Now, TLS almost does this, but TLS protects connections, not messages. As soon as the message hits the other end of the connection, it's unprotected again, and that intermediate server can see the message, it can alter the message, it can delete the message. It doesn't have to even deliver it. In order to really get what we want, we're going to have cryptography at the application layer in the source and destination clients. And that means cryptography in the browser if we're doing browser-based clients. Now, in a regular traditional client, you could possibly get rid of TLS and just use your own application level encryption. But it doesn't really make sense to me to give up that extra layer. You might as well use it. And in any case, in the browser, you really need to continue to use TLS because your code's being delivered dynamically. And if you don't have TLS, your code can be subverted before you even get a chance to run it, and you have no idea if it's secure. So we started out and we said, we have a particular business problem that we want to address. We build software for government transportation agencies. DOTs like Caltrans use our systems to manage their construction programs. And part of the construction program is handling the bidding. The DOT prepares a specification of a proposed construction project. Contractors take that specification and prepare bids. They print their bids, seal them in an envelope, drop them in a lockbox at the DOT. They could, in theory, mail those bids in, but in fact, they all actually go to the DOT and drop them off because they're negotiating with their subcontractors and suppliers till the very last minute. That's an expensive proposition, but they do go to the DOT, and then at the bid deadline, they go to the DOT auditorium. As I mentioned, my goal was to protect data going between two browser users in transit, including at intermediate servers, something that TLS and SSL can't quite do for us. So we're going to have to put cryptography in the web browser, and we want to know the best way to do it. And as I was mentioning, we also have to deal with the fact that we're dynamically delivering code to that browser, so we still need to protect it with TLS. I talked about our business. We do applications for DOTs to manage their construction programs, and contractors bid with the DOTs, but they weren't using our software. They're not part of the DOT, they're outsiders. So they'd prepare their bid on paper, seal it in an envelope, put it in the Dropbox, and then, this is where I was, you guys are all caught up to me now, and then at the bid opening day, they all go to an auditorium, they see the envelopes taken out of the Dropbox, and the envelope's unsealed in front of witnesses, and the bid's read out loud, and they find out who's going to have work to do in the coming months or years. Well, as I mentioned, this is an expensive proposition for the contractors. They have to take people out of the office for a few days. If they're not based in the state capital, they have to travel and usually have hotel bills. And we looked at this and we told the DOTs, we've been building you software for your own internal use. Why don't we create a service for you to work with the bidders with? We created one on the web, called it Bid Express, and the idea was that the DOT will issue an electronic specification of the job. The contractors will use a Windows computer program to fill in their bid, send it back to our server. Our server holds onto it till the deadline, so it acts as a lockbox, and then the DOT would receive it. Now, that's not quite good enough. The bid is not sealed against us, so we use public key cryptography. Before the bid leaves the contractor's PC, it's encrypted with the DOT's public key, and only the DOT has the matching private key to decrypt it. So while it's on our server, it's held sealed from disclosure. Those envelopes, though, that seal bids do another thing. They protect the bid from being tampered with, too. So we gave that, we solved that problem also with public key cryptography with digital signatures. Every contractor that wants to use this service has to create a key pair, register their public key with us, and we verify their ID. And then when they submit a bid, we can verify who the bid came from and that it wasn't modified. We went live with this service in the last century, in 1999. And it went live with a single DOT, Georgia DOT. And it worked pretty well from the beginning, but it took a couple years before yet another state even tried it. However, we now have 3/4 of the state DOTs using this system. The vast majority of federal aid, highway, and bridge jobs being bid through this system, as well as some other transportation agencies, and we've recently branched out to non-transportation agencies as well. We just passed a milestone. We've processed $1 trillion in bids through our service. So we're really pleased with it. Contractors are saving a lot of time and money, so they love the service too. DOTs are getting better prices because this has increased the number of people bidding because it's lowered their cost to bid. So everybody is pretty happy, and it went that way for a few years until we started being asked, web browsers are getting pretty powerful. Why can't we just do our bidding inside the web browser instead of having to install a Windows program? Now, it wasn't that they didn't want Windows. We've never had a contractor say we want Linux or Mac, although lately we've been getting them saying we want to do it on iPads. But it was that we just don't want to install software, have to keep it up to date. Can't we just work in a browser? And we wanted that as well. But there were problems. The browser wasn't too capable at first, but now a browser can do everything that we need for the bidding client with one exception. It couldn't do cryptography. And the reason is that JavaScript and the browser VM are really not very well suited to doing cryptography. It's a sandbox that doesn't have a lot of entropy, so you have a problem getting good random numbers, which a lot of cryptographic algorithms need. JavaScript is relatively slow, and yeah, it keeps getting faster, but public key cryptography itself doesn't. That's already a slow process. JavaScript didn't have features that allowed it to easily work with really large integers, 1,000-bit long integer, that sort of thing, and their arithmetic. It just wasn't a good environment. It certainly wasn't someplace that we wanted to implement a crypto library in. Well, there have been people who have been developing crypto libraries in JavaScript. It is possible. But we still weren't too comfortable with them. They were new libraries. They hadn't had a lot of separate review. What we really wanted to deal with was libraries that had been used for years, had been reviewed by a lot of people, and had perhaps had failures that had been found, patched, and fixed. We want to use the existing time-tested libraries that the browsers already have for TLS. Every web browser out there has a library that does all the crypto we need. It just doesn't let us access it from JavaScript. Well, that's not true anymore. The W3C, a couple of years ago, formed a web cryptography working group, and that group just issued a candidate recommendation last December for a web cryptography API. And although the spec doesn't tell the browser vendors, here's how you implement it, the reality is what they're all doing is they've created an API that lets our JavaScript ask the underlying TLS crypto libraries to do our cryptography for us. It is really getting implemented quickly. It's already live on Chrome and Firefox and Opera. And it exists on Safari and Internet Explorer, but it's incomplete and behind a vendor prefix. Still, the fact that they've already started it is a good sign that they plan to actually support it. It's on every operating system that these browsers support. I've tested this on Linux and Macs, Windows, Android, Chrome OS, Firefox OS. It even runs on a Chrome web browser on this wristwatch. So we now have the theoretical ability to write a solution that can be totally platform independent and still do the kind of cryptography we need. That is really great from our point of view. So we looked into it and said, how are we going to use the API? And the API lives in the window.crypto object. So it is a DOM API. It's provided by the web browser. It's not part of the JavaScript language interpreter. And this object has a single method called getRandomValues. That takes a chunk of memory, fills it in with good random data, seeded with entropy from the underlying operating system, and returns that chunk of memory to the calling program, which is great. If we wanted to implement our own crypto libraries, we now have a nice source of randomness. We don't want to do that. Well, we actually get the cryptography we want in a child object, window.crypto.subtle. This object has a dozen methods. And those are the methods that do everything we want. These are the methods that can encrypt and decrypt messages, digitally sign and verify digital signatures, do message digests, and then a variety of methods for managing keys, creating them, importing them, exporting them, and so forth. This is exactly what we want. Although, when we first started it, we really were wondering, why is it called subtle? There doesn't seem to be anything subtle about the API, and there really isn't. The reason they called it subtle, according to the specification, is that they're worried that programmers who don't understand what these cryptographic algorithms do are going to use the library, get cryptographic output, but have it not be secure, have it be stuff with vulnerabilities easy to crack. So they're calling the API subtle crypto to put all of us on notice that if you're going to use this API, do a little bit of research into what you have to give it for parameters. Don't just throw anything at it because it might make a big difference. Well, we wanted to start using it, but the only documentation on the API was the API specification itself. And last week, Peter Paul, I'm not sure if he's Koch or Koch or what, but anyway, the guy who writes Quirk's blog about mobile CSS and a lot of other things related to mobile, published a rant on his blog. He was trying to understand some W3 specs and found them unreadable. And he wasn't even trying to learn how to implement programs using an API. He was just trying to figure out what the browsers were supposed to be doing in certain cases. This is what we found with the Web Crypto specification. I opened it up. It's over 100 pages long. It looked like total gibberish to me. And for that matter, it was very redundant gibberish. I'd flip through it and I'd say, didn't I just see this paragraph? And in a lot of cases I did. They actually copied the documentation for all the different cases they had to handle. Every now and then I'd see something that made a little sense to me, but not much. Wasn't the end of the world. I'm not one to read a manual anyway. To me, that's a last resort. So I decided to just jump in and try and use the API. The problem I tried to solve was the simplest thing I could think of with cryptography, doing symmetric cryptography. Now, we want to actually get to public key cryptography and digital signatures, but this is certainly a starting point. You take some data that's called plain text, a bit string that is a key, and the encrypt operation transforms it to ciphertext. And it's symmetric because you can take the ciphertext and the same key and use the matching decrypt operation to get your original plain text back. I saw what the dozen methods were, and I figured, obviously, I'm going to use the encrypt method. What I didn't know is what parameters it took. So it was back to the spec, not really understanding it, but eventually finding something that showed that this method takes 3 parameters, an algorithm identifier, a key, and some data. So I wrote 5 lines of JavaScript, pasted it into the Chrome Dev Tools, which, as of last summer, were actually supporting this API as long as you set a flag to turn it on, and gave it a try. Now, this is 5 lines of code, and I suppose I should take the glass half full point of view, because one of the lines was right. All the others were wrong. But the neat thing is, in figuring out what was wrong and how to fix it, by the time I was done with that, the spec started making a lot more sense. I had some context to it. It kind of reminded me when I studied Russian in college, which didn't even have familiar-looking letters. It looked like just artwork until I started to learn a little bit of it, and then it got faster and faster. That happened here as well. So my hope is, by the end of this talk, after we've gone through this, any of you that want to go and use this API will be able to. Is there a question? Oh, it's okay. Well, the encrypt method is the right method, but it doesn't return the ciphertext. Encryption can take a long time. It happens outside of the browser in the external library. So obviously, the API writers made it asynchronous. But I didn't notice it was asynchronous because there wasn't a callback parameter being passed to it, which is how I recognized them. Well, they're using a new JavaScript way of handling asynchronous methods called promises. The encrypt method returns a promise, which is a JavaScript object that we can give a callback to later. Doesn't sound like it's going to be too hard to adjust. The algorithm identifier, turns out you don't just give it the name of the algorithm, and even if you did, this is the wrong name. AES is an algorithm that only encrypts a single block of exactly 16 bytes. If you want to encrypt arbitrarily long data or arbitrarily short data, you have to use something that's built on top of this, that also handles some of the weaknesses of reusing a key with possibly repeated data. And I've heard of that, and I know there's one called AES CBC, so I knew I had to use that. The other thing I discovered after days of banging my head against the wall is that the algorithm identifier is not just the name of the algorithm, it's a complete JavaScript object. One of the properties is the name, and then that might be it, depending on the operation. However, based on the operation, you might have to give it other properties. And after a lot of trial and error and skipping through it, I found out I needed to give it another property called IV for initialization vector. I knew enough about cryptography to know that this is something that kind of was used at the beginning of the encryption. It's random data that needs to be different every time you call it, so that even if you do use the same key for similar messages, you're not going to have anything that's easy for somebody to crack. The third problem was my key. I knew that AES took 128-bit, 192-bit, or 256-bit keys. So I randomly selected a 128-bit number and wrote it in hex and gave that to the API, and it didn't take it. Well, one of the reasons it didn't take it is that's too big to be an integer in JavaScript. It gets converted to a float. But the other reason is there's something really important in the API. Anytime you want to do cryptography, you have to use a crypto key object. And that's an object that you can't create yourself. Only the API can create it. And one of the big reasons that they require the crypto key object is it hides the actual key from the JavaScript environment. It is impossible for anything inside the browser to find out what the key is for a given crypto key. Keeps it outside of the browser. That's a nice security feature, but it does mean I'm going to have to find out what API operation can take the bits I want to have for a key and turn it into the right kind of object. And finally, the thing that I didn't think could be wrong was the plain text input. This was plain, this was text, but it's wrong. The API is very consistent in this, I found out. Every time we need to give it data, or it gives us data back, we need to give it in a form called a buffer source, which is their name for an array buffer or array buffer view. So at this point, I knew what was wrong. I wasn't quite sure how to make it right. So I did a little bit of remedial work on promises and array buffers. Can I see a show of hands of how many people have programmed with JavaScript promises? OK, then I don't have to talk much about it. How about array buffers? Not quite as many. Well, for those of you who haven't used promises, they're very simple. They're an object with a then method. You give the then method your callback. And you actually can give it two callbacks, one for success and one for failure. The reason promises are so worthwhile is that you can chain them, because the return value of calling the then method is always another promise. It'll automatically take whatever your callback does and wrap it in a promise. That makes it very easy to take multiple asynchronous operations and have them operate one after another, which is a real pain with traditional callbacks. Array buffers are actually even simpler. They're like traditional C language arrays. They're just a chunk of memory. You allocate them with the array buffer constructor and say, give me this many bytes. You've got a variable pointing to that many bytes. The problem with array buffers is, although I now have 8 bytes of data, I don't know what they are, and I can't see them, and I can't change them. For that, I have to have an array buffer view, which is also known as typed arrays. And this is simply saying, take an existing array buffer and pretend that it is a sequence of simpler types. And the simpler type that I always use is unsigned 8-bit integers, because that's what a byte is. So if I create a new view variable with the uint8 array constructor passing it the buffer, I get another variable that points to the same memory as the buffer, but now I can address each individual byte of it and change each individual byte. There is a shortcut. I don't have to create a buffer first. I can call this constructor and give it a traditional JavaScript array of simple values, and it'll build an array buffer view with those values filled in. Well, that was the only background I really needed to do this. So now I went back, and we're going to go back and do this operation right. Well, the first thing we have to do is set up 3 variables that we're going to use in the API. We know that we're going to have to give the API our key, which is a bunch of bits, but I'm going to have to stick that 128 bits into 16 bytes. The initialization vector, which has to be 16 random bytes of data, and the plain text has to contain the text, but it has to be in an array buffer or array buffer view. So these 3 lines of code all set up buffer source objects 3 different ways. The key buffer creates it with the uint8 array constructor and gives it data to fill in initially. The initialization vector is created with getRandomValues. We finally have a purpose for that. And plain text is using the new encoding API and the text encoder object to convert a string into a UTF-8 encoded array buffer or array buffer view. Of course, you might not have the encoding API on your PC, in your browser, but one nice thing about working with something as cutting edge as web crypto is if the browser supports it at all, it probably supports all the other new things too. So this is a solution for that. Time to use the API itself. Before I can encrypt, I need to get a crypto key. So I'm going to use the import key method. I'm going to give it that key buffer, the actual bits that make up the key, and I'm going to tell it what algorithm I want the key to be used for in the future, and I want to tell it what operations I want to perform with the key, which in this case are encrypting and decrypting. There are two other parameters that I had to specify. One of them is the format that the key bits are in. Now for AES, it's real simple. It's known as raw. It's just a straight sequence of bits. But if I was doing RSA or elliptic curve cryptography, the public and private keys have a lot of internal structure. So there's a standard format that you use for each of them that's in the spec. The other thing I need to do is tell it whether I want to ever get the key bits back. That's what the Boolean false is there for. Remember, once I create a crypto key, I can't see what the bits are that make up that key. But there is an export key method in the API where I can ask the Web Crypto API to give that back to me. And if I set this parameter to false, I'm telling the API, don't give it back to me even if I ask. This means that even if somebody completely subverts your code, they can't at least steal your keys once you've created them. Import key, like encrypt, and like every other method in the Web Crypto API, returns a promise. So the stuff in blue evaluates to a promise, so it has a then method, and I gave the then method a callback. The callback is going to be given the result of the import key operation, which is a crypto key. That's going to be the parameter. So inside the callback, I now have everything I need to do the encrypt operation. I have the object that describes the algorithm and any necessary extra parameters it needs. I have the key as a crypto key object, and I already had the plain text set up as a buffer source. So I can call the encrypt method, and the encrypt method itself returns a promise. Even if it didn't, though, the then would take whatever it returned and wrap it in a promise. So the stuff in blue, again, evaluates as a promise, so it has a then method as well. I give that then method a callback that's going to be passed the ciphertext, the result of encryption. And at this point, I can do whatever I want with the ciphertext. I can upload it to a site. I can let the user download it. I can use it for encrypting and decrypting, whatever's appropriate. We did two asynchronous operations, and we did them in series very, very easily, thanks to promises. Now, I'm done. This is what I set out to do. But this last then method also returns a promise, and I'm going to use that fact, not to do another operation on success, but to handle any errors. Any error that occurs in that chain will pass all the succeeding success callbacks in the chain and fall through to the very first failure callback you have. So I almost always end my chain with a failure callback. I can log or inform the user of what went wrong. By the way, I see some people taking pictures. I'm going to give you a URL, which I not only have the slides on our site, but I have a web page with lots of resources to everything I'm alluding to that I think will be useful to you. Okay, that is the core of it. If you can do that, you can probably make some sense of the spec, if you can find anything in it. That is one of the problems with it. As I said, it's over 100 pages long. So I'm going to give you a little bit of a Thomas guide to the Web Crypto API candidate recommendation. Section 19 lists all of the algorithms that the specification supports. So if you want to use something like triple DES, you're out of luck. This API doesn't have it. It's only got relatively new ones and relatively safe ones. They do say that they may add more in the future as part of a update process to the spec, but for now, this is it. So if you're going to want to do cryptography and share your encrypted information with something like OpenSSL or the Windows Crypto API, make sure the other side of that conversation sticks to this set of algorithms. Well, actually, that's a little too positive. The spec tells browser vendors that they don't have to implement any of the algorithms they don't want to. And the reason is that the browser vendors didn't write the crypto library. They're using whatever they've already used for TLS. And that crypto library may not have all of these algorithms supported. So they tell them that's okay. You still are a compliant browser, even if you don't have them. As an application developer, that's disastrous for me, because if I have a user in Chrome on a Mac encrypt a message and send it to somebody running Firefox on Windows, I want them to be able to decrypt it. And they can only do that if they have some algorithms in common. The spec does not give a minimum set of algorithms. They have said that as part of the process of browser vendors implementing it and giving them feedback during the candidate recommendation phase, they may add that before it's a final recommendation. But I went to every web browser I could find that implemented this, on every operating system I could find, and I found that all of them support these algorithms. This is a nice set of algorithms that have a public key signing, a public key encryption, symmetric encryption, some message digest functions, and a function to derive a cryptographic key from a password, a user-entered password. If you stick to these for now, you're going to be pretty safe, regardless of what browser your users have. A year from now, this page, I hope, will be completely obsolete, and they'll all support everything. The next thing is we need to know what parameters each of these methods take. And that's in section 14, which is the subtle crypto interface. And this is where I got introduced to the Web IDL language, an artificial interface definition language. This isn't JavaScript, even though the only people that are going to be using this API are going to be using it in JavaScript. They had to be generic, general purpose. But even though this isn't JavaScript, it's easy for a JavaScript programmer to read this and see that, oh, generate key is going to return a promise, and, well, they all return promises, and it takes these 3 parameters. And if I want to know more about what algorithm identifier actually is, that's a link. All that's left is knowing that if you were paying attention, the algorithm identifier isn't always the same for the same algorithm. It depends on the operation I'm doing. When I did the import key, I gave it an object with only a name property. When I did encrypt, I gave it an object with the name and IV properties. How did I know to do that? Well, every one of these algorithms has a full section in the spec, and every one of those sections has a subsection called registration. And that has what, to me, turns out to be the most important table in the whole spec. That lists all the operations that you can do with that algorithm. For each operation, it tells you what parameters you have to give it and what it returns. So we can see if I generate a key for RSA SSA-PKCS1-V1_5, sort of the obvious one you'd want to use, I need to give it an object with RSA hash keygen params in it. And I'm going to get a crypto key pair passed to the callback. If I follow the link to see what RSA hash keygen params are, I get more Web IDL. But the upshot of this is that that object not only has the name of the algorithm as a property, it also has the name of, a hash you need to use for the signing, the modulus length, which is essentially the bit length for RSA, and a public exponent. So we can create a key pair pretty easily now by calling generate key and giving it an object with those 4 parameters. The name we already saw in the spec. Hash, we can look and see what hash names are available. SHA-256 is a good choice. I know that 2048 is a common length that people use for RSA key pairs. The public exponent is the thing that kind of floored me. I don't know why they even make it a parameter. The Chrome and Opera browsers only allow you to give it either 65,535 or 3. No other values are legal. You can give it any value that is relatively prime to a random number that the algorithm ends up creating. And so if you give it a prime number to start with, you're in good shape for that. But they like these numbers, and the reason is that these numbers only have 2 bits turned on. It means that they can do their arithmetic with 1,000-bit integers much more efficiently. So you can simply take this as a constant that you'll always pass to an RSA key generation. I don't want to export it. Now the thing here is it's creating a crypto key pair, not just a single key. And this export Boolean only applies to the private key part. Whenever you have a key pair, the public key is not a secret. It's always exportable. And then I want to use this for signing and verifying. I can pass it a callback to the then method. That'll be past the crypto key pair, which is nothing special. It's not like crypto key. It's just a regular JavaScript object with 2 properties, public key and private key, that are the crypto keys you'll need to use. You could then go and do digital signatures using the sign method, and you could verify it with the verify method. Pretty straightforward. Well, we're running out of time. I had to trim this down to the core that would be useful for somebody who wants to do this getting started. But I'd like to mention 2 more things. One is, if you're going to be using digital signatures, you may want to be using X509 and cryptographic message syntax. Those don't have anything to do with cryptography, really. They just use a crypto that Web Crypto API already has. They're about packaging the results unambiguously, which would be great, except that the specification was created in the 1980s by the biggest bureaucracy in the world, the International Telecommunications Union, that is the telephone company that has all telephone companies reporting to it. And it is horrible to deal with. You could deal with it anyway with JavaScript. You could break up those messages into bytes and figure it out. But you don't have to. There's a library called PKI.js and a matching ASN1.js library that together do everything you need. They're from GlobalSign. They're reliable. I've used them. They work well. They have one tiny little problem. There's zero documentation of them. None at all. But there are good examples with it. And also, we've put together half a dozen or so examples of how to of doing things with Web Crypto API at the Infotech Inc. GitHub account, and this is one of them. If you're interested in cryptography and want to know more than just a minimum on how to use it in your programs, I just would like to recommend this online course. It's a free 6-week course from Stanford University given by Dan Benet, who's a world-class cryptographer. It's offered several times a year. When I took it a few years ago, I learned a lot, even though I'd been using cryptography for 20 years. And a new session is starting this week. Finally, I told you that all of the slides and all of the references to all the standards and libraries and everything I mentioned, plus more, is at my personal website at engelke.com/fluent. That has pointers to half a dozen or so web crypto examples in GitHub, as well as the blog posts I wrote while I was doing the examples. So if you want to see the angst I was going through and the false starts I made, you should look at some of those blog posts. Or you can just say, I only care about the final result. Well, I'm slightly over time. Sorry about that. Thank you very much.